Hello, my name is Karrar Alofari from Department of Mechanical Engineering, Engineering Mechanics, Michigan Tech. My research is related to study water management in proton exchange membrane fuel cell. Fuel cell is one of the promising technology which characterized by high efficient energy conversion and a non-emission device that can be used in many applications like energy generation, transportation, and other many applications. This technology facing two main challenges, which is reducing the cost and improving the durability. The figure here shows the main components of the fuel cell. To the left is the anode, where hydrogen oxidation reaction occur. In the middle is the membrane, an electrolyte to conduct protons to the cathode, which is where oxygen reduction reaction occur, and the product will be water vapor. Both anode and cathode are made from catalyst layer, which is a porous layer, has a complex structure of carbon support, ionomer films, catalyst, which typically platinum, as well to the pores to transport oxygen and liquid water outside the catalyst layer. As the water vapor start condensing, the performance of the fuel cell degrading. One more complexity to the structure of the catalyst layer is ionomer films retain water and dissolves. The retention of the water in the ionomer films is represented by the water content lambda. As we see here in the figure, as the relative humidity increases, the water content increases. Up to 60%, there is a sudden increase in the water content. So we are using an experimental setup to study the relative humidity effect on liquid percolation throughout the catalyst layer. Since water retained by ionomer films, we are using a fluorinert liquid, which is not retained by ionomer films. The catalyst layer compressed here and conditioned using gas nitrogen, which already can be humidified using the humidifier here at specific relative humidity. After 3 hours of conditioning, the liquid fluorinert injected to start the test. Two data are recorded, the percolation pressure and the wetted area, and they are synchronized to specify the beginning of the percolation when the liquid starts invading the catalyst layer until the end of percolation when the catalyst layer reaches the sample edges. The result shows as the relative humidity increases, the percolation pressure increases. From 5 to 40% relative humidity, there is a gradual increase. However, at 60%, 65% relative humidity, there is a sudden increase, which is consistent with other high relative humidity tests. This result is more likely consistent or related to the relative humidity effect on water content. More than 60%, we can see here there is a sudden increase. Also, by specifying the beginning and the end of percolation, we can see the high difference between high relative humidity and low relative humidity. So these results can give insight to understand the liquid percolation through the catalyst layer and improving the performance of the fuel cell. At the end of this video, I'd like to thank my advisor, Jeff Allen, and also my co-advisor, Ezekiel Medici. This work supported by Department of Energy and the HCED. Thank you for listening.